Hello again. So there's a new release of the sharkC64 compiler. The version number is now 0.2. And as the new thing, it has assignment statements and module initialization. So I was thinking that I would show you today how the compiler works. And as an example, I'm going to use assignment statements. So sharkC64 is a multipass compiler. It doesn't generate directly bytecode from the source code. Instead, it takes the source code and refines it in a stepwise manner to a bytecode. So let's see how that works. This is the processing chain for the compiler. It has 5 steps: a lexer, a parser, a binder, a translator, and a generator. Suppose we have an assignment statement in the source code. In technical terms, it is a sequence of characters at the moment. The sequence of characters is first given to a lexer. It groups the characters into a sequence of tokens. So the lexer sees the first letter, A, and as it's followed by a non-letter character, the lexer deduces that it is a label. Then the lexer continues to read the next character. This is a non-letter character, and as it's followed by another non-letter character, the lexer considers them both at the same time. In this case, the 2 characters form an operator, and that is recognized by the lexer. Next, the lexer recognizes the left parenthesis as a separator. After that, it reads a $sign that indicates the beginning of a hexadecimal number. Then the lexer collects all the numerical characters together, and that is then recognized as a literal. After that, lexer continues reading the characters and grouping them into tokens until all the characters are processed. As a result, we have now a sequence of tokens. That is then given to a parser. It builds a syntax tree from the sequence of tokens. So the parser looks at the first token in the sequence. In this case, it is a label. The parser picks it and moves on. Then the parser recognizes the next token as an assignment operator. It picks the operator and starts forming a syntax tree for an assignment statement. In the syntax tree, the left branch has to be a variable. As the parser has already picked it, it can be linked to the syntax tree. The right branch of the syntax tree has to be an expression. The parser now knows that the rest of the tokens represent an expression. The parser continues reading the tokens. Here the first token indicates the start of an inner expression. The parser notes that and continues then reading the tokens for it. In the inner expression, the first token is a constant. The parser picks it. The next token represents an addition operator, and the parser picks it and links it to the constant. Then the parser reads the next token, which is a variable. The parser picks the variable as well. As the next token indicates the end of the inner expression, the parser links the collected variable to the addition operator. Then the inner expression has been processed, and the parser continues reading the remaining tokens. The next token indicates a conjunct operator. The parser picks it and links it to the addition. The next token indicates again an inner expression, and the parser continues processing it similarly to the first inner expression. After the inner expression has been processed, there are no more tokens left. Then the parser links the collected inner expression to the conjunct, and the conjunct is then linked to the assignment as the expression. And now we have the result, which is a syntax tree for the assignment statement. It is then given to a binder. It builds an object graph from the syntax tree. In the object graph, all the variables are bound to object instances with type information. So in addition to the syntax tree, the binder has a variable space. The variable space consists of variables that have been already defined in the program. Then the binder maps all the variables in the syntax tree to the corresponding object instances in the variable space. In addition to the variable space, binder has also a type space. The type space consists of type instances that have been defined. In fact, the variables must already have been bound to type instances when they were defined, so those bindings exist already. The binder still has to bind constants to their types, and in doing so, it has to also verify that the types match in the expression. So now we have an object graph for the assignment statement. It is then given to a translator. The translator turns the object graph into a program fragment by using an intermediate representation language. To do this, it has to consider the context and define temporary variables when needed. So as the first thing, the translator defines the variables. Next, the translator analyzes the object graph to identify which temporary variables are needed. In this case, there are two temporary variables that are needed to compute the expression. Then the translator starts translating the expression from left to right. Lastly, the translator adds the instruction to store the result to the variable. So now there is a program fragment describing the assignment statement, and it is expressed by using the intermediate representation language. Just as a side note, the intermediate representation is not text. It is actually an object tree, but to keep the presentation clearer, I show it here as text. The program fragment is then given to a generator. It generates the final byte code. Here, instead of the real byte code, I'll show assembler code. It is easier to read it. The byte code is generated instruction by instruction. This is perhaps the most mechanical step in the whole compilation process. So now we have finally compiled the assignment statement to bytecode. So that was the story of the assignment statement, or actually the compilation of an assignment statement. So there's a new version of the sharkC64 compiler available in GitHub, and I put the link into the description if you want to try it out. So thanks for stopping by and see you soon. Yeah, the floor looks okay. I suppose I could add walls as well.